Okay, in the previous video, we basically had a discussion regarding the periodic property, the periodicity of a continuous time and discrete time sinusoidal signal. And there was a additional restriction in discrete time case wherein the time period had to be the number of samples. So it had to be an integer. And just to elaborate that particular point, there's a small problem, small example, although we will be doing a lot of examples in the tutorial session, but just to convey the concept. So it says that a sinusoidal signal in the discrete time domain, it is defined as this: x of n is equal to sine of 5 pi n. And we have to specify the condition which the period n of this signal must satisfy for the signal to be periodic. Fine. First, had it been something like this, a signal in the continuous time domain, x of t is equivalent to, say, sine of 5 pi t, then it was periodic. It was implicit, that it was implied that this is periodic. So with some time period, you can go and just see what the time period was, but this was periodic. There was no question about it. But here we have to come up with a condition. It's not implied that if I have a signal, let me just rub this off, that if I have a discrete time signal x of n, it is sinusoidal, but it is not implied that this is periodic. We have to check on the condition first to see whether it will be periodic, and then under which conditions this will be periodic. So this is a typical example which will help us to understand the concept in a better way. So let's just compare it with the general form of a sinusoidal signal which we did. So I'll do one thing just to avoid confusion, although it doesn't make much of a difference. Instead of sine, I will put cosine. Fine, because the general description that we did in the last video, it was in terms of this cos. Fine, although it doesn't make any difference, you can always replace cos with sine, the properties won't change. Fine, so it's not that big a deal, but just to be consistent as to what we have been using up to this point, I will replace sine by cos. Okay, fine. So our general description, a cos, and then I think it was omega of n plus phi. So if you compare this and this, obviously amplitude is unity, we're not bothered about that. It doesn't have a phase angle, phi is 0, but our comparison gives us that omega n is equivalent to 5 pi n, so which means omega will have a value of 5 pi. Right? Now the condition for periodicity is this, that is, n should be equivalent to 2 pi and some integer small m divided by the angular frequency. Now if I substitute it here, turns out n will be 2 pi m, and for for omega, I keep saying it is phi. Fine, so ye aur ye jayega, so I will have n is equivalent to 2 by 5 into m. Now clearly this is a fraction. Fine. Now for xn to be periodic, n should have a discrete value. N must be an integer. This is the basic fundamental condition in the discrete time case कि जो आपका time period है, it has to be an integer value. It cannot be a fraction. Right? Now it is possible only when, so let me just complete the statement so that it is more clear here. So which is possible only when m has a value of 5, 10, 15. In general, you can say multiplies of what you call 5, because let's suppose in this case Now that we have found the time period 2 by 5m, if m has a value of 5, then n is equivalent to 2. Similarly, if m has a value of 10, then n will have a value of 4. Fine. So this becomes the condition then, that it's not implied that this will always be periodic. There is a special condition on the time period under which it will be periodic. So whenever your m has a value of 5, 10, 15, that's multiples of 5, then only your this discrete time sinusoidal signal, this one, it will be periodic with the period 2, 4, 6, 8 जो भी आएगा, ठीक है. And if this condition is not satisfied, if I have any arbitrary value of m, say m is equivalent to 2, then n is equivalent to 4 by 5, which is a fraction, it's not an integer. So under those conditions, जो आपका discrete time sinusoidal signal है, it cannot be periodic. So this was just a quick example in between, just to clarify this particular point, that when it is continuous time domain sinusoidal signal, it is implied it is periodic. It will definitely be periodic, and you can find out the time period using this relationship. But if it's a discrete time sinusoidal signal, it's not implied that it will always be periodic. You have to do a bit of analysis and come up with a condition under which conditions and under what conditions this signal is going to be periodic. Fine. Okay, this was about sinusoidal signals. So if you remember in the previous video also, I told you that our exponential signals, they can also be complex. I mean, if you quickly go back here, so we had two parameters, the amplitude of the exponential and the actual exponentiation factor. So we had assumed here that both these quantities are real valued, but in general, one of the quantities, both the quantities, they will be complex valued. So fine. So here will be just considering, although it is a part of exponential signal, but I will list it as a separate. So this is again an exponential signal, but this time round we will be analyzing complex exponential signals. And we basically express these exponential signal in terms of sinusoidal signals. Now that we have defined the nature of sinusoidal signal, it will be easy to express a complex exponential signal. So again, I will start with the general description. So generally speaking, complex exponential signal, it will be of this form, that x of t is equivalent to b e raised power. Now the exponentiation is complex, fine. And the quantity b, which defines the amplitude of the exponential, it's also a complex quantity. So let me just put out here that b may also be complex, that it will be of this form, fine. Then x of t, which is equivalent to b e raised power j omega t, it will be actually a e raised power j phi into e raised power j omega t, right? And if I combine, so it will be a e power, so j, I will keep common, omega t plus phi, fine. This will be my complex exponential signal. Now there is a formula, again you must have done it in your trigonometry course. We call that the Euler's identity, that e raised power j theta is cosine of theta plus j sine theta. Right? This is a very famous identity in complex as well as in this trigonometry. So if I use this here, so then x of t, it will be a, first we will have the cosine component, cos of omega t plus phi. Then we'll have the sinusoidal complex component, sine omega t plus phi. Okay. In other words, I can say, if I compare real and imaginary parts, that the cos component, a cos omega t plus phi, it is basically the real part of x of t in general, can say like this. Okay, so the real part of the first, a complex exponential, it will have a real part and imaginary part, and then you can express this as a in terms of cosine and sine components. So here the real part of the complex exponential is represented in terms of the cosine. But similarly, you can say that a sine omega t plus phi, and this will be the imaginary part of this be j omega t. So you have basically decomposed your what you call this a complex exponential into cosines and sine functions. Since we already know the nature of these two functions, like they are periodic, they may have amplitude and all that stuff, so you can very well express the complex exponent, and it is much easier to express a complex exponential in terms of its sine and cosine components. Fine. And the generalization is valid for the discrete time case also. So in discrete time, we may write that a cos omega n plus phi, it will be the real part of the complex exponential, and a sine omega n plus phi, it will be the imaginary part of your complex exponential, where the quantities have their general meanings and the properties, they will still stand. Mean the periodicity, it will again follow that particular property of that we discussed prior to this. Fine. So this was about complex exponential signals. Additionally, we have a kind of a combination of two signals, and again in control system they are often encountered. We kind of what you say, try to kind of express the behavior of a system sometimes in terms of these signals. And one frequently encountered signal is what's known as exponentially damped sinusoidal signal. Right? You learn about these things in detail in your control system and network synthesis. So it is basically a product of your exponential signal and a typical sinusoidal signal. So this will be typically a signal of this type, x of t. It will have the exponential factor, say e raised power minus alpha t, that will modulate the sinusoidal function. Right? So the amplitude of the sinusoidal is modulated by an exponential signal, and it will have an impact on the nature of the signal. Fine. So if I typically plot it, normally your what you call pure sinusoidals, they have sustained oscillations. But just a second. So your normal sinusoidal, it will have a sustained oscillation, something like this. The amplitude will not vary, ideally speaking. Fine. So this will be a pure sinusoid, say sine omega t plus phi. Fine. But when it comes to this exponentially damped sinusoidal signals, if you can see, this is basically a decaying exponential. So it will impact the amplitude of my sinusoid. So it will be something like this. I'll try to just something like this. It will reduce its amplitude continuously as the time goes on. Fine. So physically speaking, whenever these signals are generated by the source, there is a tendency that this is a more practical case, because you can't have the oscillations, sinusoidal signal generated from a physical source. They cannot sustain. After some time they will die out. Fine. For example, there's a large thud. Some blast is the some bomb blast occurs at some instant. So gradually the sound will decrease. First it will be a big thud, and obviously the waves that are associated with the sound, they will also decay as the time goes on. Okay, so this is a more practical case to say that it is an exponentially damped sinusoidal signal. So इसका जो envelope होगा, that will be an exponential decay, this decaying exponentially. Fine. So the general thing is that the exponentials and sinusoidals, they can interact in a number of ways. Similarly, you may have exponentially growing sinusoidal signal, wherein a sinusoidal signal is multiplied by a growing exponential, and the amplitude will go on increasing with time. Right? So you can't have different combinations. Right? But in general, this is how we express it. If it is a pure complex exponential, you'll have the general properties. If it is complex, it is better to decompose your complex exponential signal in terms of sinusoidal signals and then do the analysis in terms of sinusoidal signals. So I'll stop here. We have some other signals to discuss that will be in subsequent videos.